Let us have a look at this question. If you can have a look at this question clearly, this question resembles the previous question we have solved just before this. Okay, here. As in the question, a processor has 16 integer registers and 64 floating point registers. The processor has 16 integer registers and 64 floating point registers. Okay, there are two different kinds of register sets available in the processor. Those are 16 integer registers and 64 floating point registers. Keep it in your mind. It uses a 2-byte instruction format, meaning in this processor, the size of an instruction is equal to 2 bytes, 16 bits. I have written here the size of the instruction in this processor is equal to 2 bytes, which is equal to 16 bits. There are 4 types of instructions in this processor, namely type 1, type 2, type 3, and type 4. Look at each type and what it is all about. Type 1 instructions has 4. Total number of type 1 instructions are equal to 4. And this type 1 instruction has 3 integer register operands. In type 1 instructions, we can have 3 integer register operands. We will see how does it work in a short while. There are a total of 8 type 2 instructions. You can see type 2 category consists of 8 instructions, each with 2 floating point register operands. Let us see. There are a total of 8 type 2 instructions. And these type 2 instructions will have 2 floating point register operands. Okay. Now, when it comes to type 3, there are altogether a total of 14 instructions. And these type 3 instructions have 1 integer register and 1 floating point register operand. That means that in type 3, in addition to the opcode, I do have 1 integer register operand and 1 floating point register operand. When it comes to type 4, there are a total of n number of instructions. We need to find out n, what is n, each of with a floating point register operand. That's it. Each of with just a floating pointer register operand. Okay. Now let us have a look at all these types of instructions again. Type 1, the total number of instructions are equal to 4, and these instructions have 3 integer register operands in addition to the opcode. When it comes to type 2, we do have 8 instructions, and this type 2 will have 2 floating point register operands in addition to the opcode. Type 3, total 14, and in addition to the opcode, we do have 1 integer register and 1 floating pointer register operand. Type 4, we need to find out the number of type 4 instructions, and this type 4 instruction does contain 1 floating point register operand, and then that's it, only 1 floating point register operand. Let us see how does it work and how we need to solve. Okay, there are 4 types of instructions. This is type 1. I will write it here. Type 2, type 3, and type 4. What is the size of the instruction? Size of the instruction as it is given in the question, is equal to 16 bits, right? Size of every instruction is equal to 16 bits, 16 bits, 16 bits, and 16 bits. All right. Now, let us go to the type 1 instruction. When it comes to the type 1 instruction, in addition to the opcode, I do have what? 3 integer register operands. In order to find out how many digits are required for each integer register operand, just have a look at the total number of integer registers in the system. The total number of integer registers in the system is equal to 16. I will write it here. I will write it here. Integer registers in the system is equal to total 16. So for one integer register field, I do require 4 digits because 2 power 4 is equal to 16. So when I use 4 digits, these 4 digits will be sufficient to represent one of the 16 integer registers in the system. Okay. Now, when it comes to type 1, I do have, in addition to opcode, I do have 3 integer registers. I will write it here. Integer register field 1, integer register field 2, and integer register field 3. So how many digits for each field? Each of the integer register field will take 4 digits each. 4, 4, 4. That means that opcode will have also 4 digits. Total is equal to 16. Okay. So integer register 1, integer register 2, integer register 3, altogether they will consume 12 digits. So now 16 minus 12 is equal to 4 digits. Those are used in the opcode field. Okay. Now, these 4 digits, as you know, will give us 16 combinations, right? So 4 digits will give us 16 combinations. But are we using all the 16 combinations? No, we are not using all the 16 combinations because type 1 instructions are just 4. Okay, there are only 4 type 1 instructions. That means that out of 16 available combinations, I'm using only 4 combinations because type 1 instructions are just equal to 4. So total 16 combinations are available in opcode, that is from 0000 to 1111. But I do require only 4 combinations to encode all the opcodes in type 1 instructions because they are just 4, which leaves us 12 unused combinations in the first 4 digits after encoding the type 1 instructions, after designing type 1 instructions. So what I can do is, I can use these 12 combinations to encode the type 2 instructions in the first 4 digits. Okay, let us come to type 2 instructions. The type 2 instructions, if you can have a look at, these type 2 instructions are equal to 8. Okay, there are a total of 8 instructions. Type 2 is equal to 8. Okay, so now type 2 instructions uses 2 floating point register operands. 2 floating point register operands. So in order to understand how many digits that are assigned to one floating point register operand, we need to identify the total number of floating point registers in the system. The total number of floating point registers in the system is equal to 64, as you can see here. That means that if it is a floating point register operand, I will write it here. FR is equal to 64, in which we do require 6 digits to represent one floating point register field. In type 2 instructions, in addition to this opcode, I do have FR1, floating point register 1, and floating point register 2. So each field will take 6 digits each. Okay, 6 plus 6 is equal to 12. Now here the opcode in this case is also equal to 4 digits as in the type 1 instructions. Now these 4 bits will give us 16 combinations. But out of the first 4 digits, out of the first 16 digit combination, the first 16 combinations out of the first 4 digits, 4 combinations are already used, right? We have got just 12 combinations because type 1 instructions and type 2 instructions both has the 4 digits in the opcode. Okay, but after encoding, after designing type 1 instructions, we are left with only 12 combinations in the first 4 digits to design my type 2 instructions. Right? Now, the type 2 instructions are equal to 8. Right? As the type 2 instructions are equal to 8, these will consume 8 out of 12. These will consume 8 out of remaining 12 in the first 4 digits after encoding type 1 instructions, which are equal to 4. Okay, so here, after designing 8 type 2 instructions from the available 12 combinations, I can have 12 minus 8, which is equal to 4, still available, and we can use these 4 combinations to design type 3. Okay, first 4 digits and the first 4 digits, type 1, type 2. These digits are opcode for both type 1 and type 2. These first 4 digits giving us 16 combinations, out of which 4 are used by type 1 and 8 are used by type 2. So after encoding type 1 and type 2 instructions, the first 4 digits are still left with 4 combinations. I will use these 4 combinations to encode and design the type 3 instructions. But when it comes to type 3 instructions, if you can see, these type 3 instructions has one integer register operand, one floating point register operand. So there is one IR, integer register operand. There is one FR, floating point register operand. You know the number of digits that are required for IR, which are equal to 4. You know the number of digits that are required for FR, which are equal to 6. Now, 6 plus 4 is equal to 10, right? So the opcode should be equal to 6 digits in the type 3 instructions. In type 3 instructions, the number of digits that are assigned to the opcode is equal to 6, because here we do have 2 fields. One is IR and one more is FR for the operands. So the FR field will take 6 digits, IR field will take 4 digits, after which we are left with 6 bits. So the opcode is equal to 6 digits, in which we need to do a practice, that is 4 plus 2. 6 is equal to 4 plus 2. Why we are dividing it to 4 plus 2? Because in the first 4 digits, some combinations are already used in type 1 and type 2. All the combinations are not available. Some combinations are already used after encoding type 1 and type 2 instructions. And the next 2 digits in the first 6 digits are being used for the first time as the opcode. These 2 digits we are using for the first time as the opcode. Earlier, these 2 digits were part in something, some different thing, that is the operand field. Now, for the first time in the system, we are using these 2 digits in the first 6 digits as an opcode, which will give us a total combinations of the number of opcodes that are left, the number of combinations that are left, even after encoding type 1 and type 2 are equal to 4 into these 2 digits will give us 2 power 2 combinations, right? 4 into 2 power 2, which is equal to 16. The total number of combinations available for type 3 is equal to 16. That is leftover 4 combinations from type 1 and type 2 and available 2 bits in the first 6 digit for type 3. Total is equal to 16 combinations. There are a total of 16 combinations possible for encoding and designing type 3 instructions. But type 3 instructions are equal to just 14. If you can have a look at, there are 14 instructions. Okay, so in the first 6 digits, after encoding type 1 and type 2 and type 3, we are still left with 2 more combinations. Okay, the total possible combinations for the type 3 instructions is equal to 16, but total number of type 3 instructions are equal to just 14. So available combinations minus used combinations in the type 3 instructions is equal to 2, right? These two combinations are still unused, which can be used to construct type 4 instructions. Okay, so when it comes to type 4, just have a look at type 4 instructions. We need to find it out. Okay, and this type 4 instruction has only one operand, that's the floating point register. If it is a floating point register, it will take 6 bits. If it takes 6 bits, opcode will be constructed by using 10 digits, right? Which should be divided into 6 plus 4. Because in the first 6 digits, some combinations are already used by type 1, type 2, type 3. After encoding type 1, type 2, type 3, we are left with 2 combinations in the first 6 digits. But in the next 4 digits, each and every combination is available, right? Because this is for the first time we are using these 4 digits for an opcode. Earlier, these 4 bits are a part in some operands. Now this is the first time we are using these 4 digits in the system for opcode. So these 4 digits are never consumed, are not occupied for an opcode. Total combinations in these 4 digits are available. So that means that the total available combinations for type 4 is equal to leftover combinations from the previous types of instructions, those are equal to 2, and the available combinations in this case is equal to 2 power 4, which is equal to 2 into 16. 2 power 4 is equal to 16, that is equal to 32. The answer will be equal to n is equal to 32. Okay, just have a recap. That is, there are type 1, type 2, type 3, and type 4. Type 1, 4 fields, 1, 2, 3, 4. Register, register, register. 4, 4, 4. Opcode is also equal to 4. Type 2, floating point register, floating point register. So 6, 6, 4. Type 3, floating point register, integer register. So the opcode is equal to, 6 plus 6, this is 6, this is 6, this is equal to, this is 4, this is equal to 6. Finally, there is one floating point register, there is, the opcode. Just have a look at type 1. In type 1, total 2 power 4 is equal to 16. But type 1 instructions are just equal to 4. So 16 minus 4 is equal to 12. So I can use these 12 combinations for encoding type 2 instructions. Okay, for type 2 instructions also there will be only 4 opcode digits. Out of 4 opcode digits, only 12 combinations are free after encoding the type 1 instructions. So total type 2 instructions are equal to 8. So 12 minus 8 is equal to 4. So in the first 4 digits, there are still 4 combinations left, even after encoding type 1 and type 2. So in the first 4 digits, we are left with 4 more combinations. These 4 combinations I will use to encode type 3. Okay, type 3. Type 3 is equal to a total of 14 instructions. Okay, so these 6 digits must be divided into 4 into 2. Okay, that in the first 4 digits, I'm left with 4 combinations. Okay, in the next 2 digits, I'm left with total 2 power 2 combinations. That is, 4 into 2 power 2 is equal to